Welcome to Hot Chips 31. Session 7, Interconnects.
My name is Jan-Willem van der Waard. I work for Cypress Semiconductor, and I will be your session chair. We've got two speakers, both of whom will try to convince you that the future of interconnects is optical. First speaker is Pat Knebel. He's a fellow at HP Enterprise in Fort Collins, Colorado. He's got over 30 years of experience designing processors, chipsets, and systems. Most recently, his focus areas include chipsets implementing the Gen Z protocol and advanced optical interconnects for high-performance computing. He's got a bachelor's from Purdue and a master's from Stanford, both in electrical engineering. Let's welcome Pat.
Thank you very much. Hi, my name is Pat Knebel. I'm an HPE fellow, and I'm here to talk about the Gen Z chipset we developed for high-performance computing and Exascale. As far as the agenda goes, we'll start with a couple slides on background, then we'll move into the silicon solution, talk about performance, and then we'll end with status and next steps. So we built this chipset for high-performance computing and Exascale, which is 10 to the 18th operations per second. And there's lots of reasons why the world is in the pursuit of Exascale. Right? Think about weather prediction. Right? Better modeling can save lives in the face of natural disasters. Or think about life sciences. By better modeling the human genome, we can make terrific advances in the fields of medicine and biotechnologies. So this work was all done at Hewlett-Packard Enterprise, and it was funded in part by the US Department of Energy under the Path Forward contract. So we built this chipset for high-performance computing and Exascale, but we had to satisfy the needs of our enterprise customers as well. HP has a very broad portfolio, and these technologies need to extend the range of that portfolio. So big data analytics, machine learning, simulation and modeling, these are just a few of the applications that our customers are running that have these data-intensive workloads. So as they adopt more of these workloads, these data set sizes are providing computational intensity, and they're putting tremendous bandwidth demands on the interconnects for these applications that have lots of node-to-node traffic. So as customers adopt these workloads, they're seeking unified infrastructure that can handle all the requirements for these variety of workloads. So what we're seeing is that technologies you might traditionally associate with HPC, those are becoming common in enterprise data centers, and that's increasing the volumes for the technologies that I'll be describing today. So as we set out to build this chipset, we needed an interconnect protocol for both HPC and enterprise, and we found Gen Z to be an excellent fit. For those who aren't familiar, Gen Z is an open, industry-standard protocol, and it's great for connecting together CPUs, memories, accelerators, storage, and general-purpose I/O. Gen Z is a memory semantic protocol, which means that load store accesses can simplify the way we do our software and our device interfaces. And it supports efficient messaging for cluster-based interconnects as well. So Gen Z can support lots of topologies, whether they're point-to-point or fabric-attached. So whether it's fat tree, folded CLO, HyperX, all of those Gen Z can support. Gen Z is secure, it's scalable, and it's reliable. And you'll be hearing about some of that as I go through my talk today. So let's dive into some of the silicon solutions. I want to talk about the system architecture, our use of optics, our use of chiplets and advanced packaging, and then I want to talk about performance. So when you think of exascale computing, you think of a room full of computers all connected together to solve the world's most complex problems. So we needed the protocol, we picked Gen Z, and then we needed the topology, right? How do we physically wire these systems together? How do we route packets from machine to machine? And we chose the HyperX topology because we found that it can give the best performance and price performance, especially when utilizing the integrated optics you'll hear about in just a few slides. So in the picture, we show a 2D HyperX, even though we expect to use a 3D HyperX for our exascale systems. So HyperX is connected all-to-all in each of n dimensions. So the picture there shows a 2D HyperX where everything is connected in the x dimension in red and in the y dimension in green. And you can imagine connecting everything in the z dimension in blue. And then we're showing multiple planes that supports extra bandwidth and availability, which I'll talk about in a subsequent slide. Now, we connect our compute to the fabric by using bridges, and you can see those at the bottom. And we need those since there are no CPUs that speak native Gen Z today. Another name for a bridge might be a NIC or an HCA. We're connecting the bridge to the CPUs using electrical PCI Express. We have 4x16 links at 16 gigabits per second. And we're connecting to the fabric with optical Gen Z. We have 12x4 Gen Z links running at 53 gigabits per second. And you might think we've over-provisioned the bandwidth on the fabric, but we use that 12x fan-out for some topology that you'll see on the last slide. Now, to build up our fabric, we have a 60-port switch, and I mentioned that it's all optical. And then you can see at the bottom of the slide, we talk about scaling to 61,000 nodes with 4 switch crossings. Or another way to say that would be 3 switch-to-switch hops in the fabric. OK, so now I want to take a closer look at our bridge module. So the picture at the bottom shows a block diagram of our bridge. And again, we're connecting to the CPU over PCI Express. And then inside the bridge, you can see we have 4 data path slices. And each of those data path slices, we have our PCI Express logic and our Gen Z logic. And the Gen Z consists of requesters, responders, memory management units, and data movers. And from there, we fan out to those optical Gen Z links with our embedded Gen Z switch. OK, so inside that bridge, we have data movers. That supports high-performance messaging between the nodes in a cluster. And it also supports high-bandwidth data movement to any fabric-attached memory that's in the system. So the block diagram on the right shows how we do some of our data movers. So we support both one-sided and two-sided messaging. In one-sided messaging, the address of the user buffer on the receive node is known to the transmit data mover. So it can simply do a direct put or get to that user buffer. And that's showed in red and green. Two-sided messaging, on the other hand, that receive address is not known to the sender. So we have to have a back-and-forth communication, or two-part communication. So for small messages, we can do what's called the eager protocol. The transmit data mover can send a single packet that contains the payload, and then the receive data mover moves that into the receive buffer, and then that's later moved into the user buffer to complete the receive. For larger messaging, we use a rendezvous protocol. And in that case, the transmit data mover sends a single packet that has a notification and an address. And then down at the bottom, the receiver has to do a get to actually complete the receive. So beyond the use of the data movers, we also support direct load store access. And what that means is that the CPU can export a load across PCI Express using extended capabilities if the processor supports it. And then the bridge can export that load or store across the fabric to any fabric-attached memory or to any memory that's local to a node. OK, so now I want to take a closer look at our switch module. So in the picture, we show one of our switch cores, and we use multiple of these switch cores, hook them together to make our 60-port switch module. So each of those switch cores is a 24-port switch core. It has 24 inputs and 24 outputs. And you can see at the intersection of every input and every output are cross-point buffers. And that's how we do our output queued crossbar. The use of those cross-point buffers simplifies a lot of things. For instance, every input has direct access to its cross-point buffer, and there's never a conflict. And similarly, when you look at the output, we can arbitrate across a column with simpler arbitration, not having to look at the whole chip. You'll notice that every input also has its own route table. And because there's dedicated route tables, we're able to achieve higher throughput for small messages. We never have to arbitrate for that route table. And like I said, our arbitration for the output is simpler as well. So even for short messages, we can sustain very high messaging rates. So inside that route table, that provides primary and secondary routes for every packet. And that's how we can build our adaptive routing. And there's basically separate tables for each virtual channel, which means that we can have separate topologies for our high-performance compute and our storage, for instance. So given that we have multiple primary and secondary routes, we can start to adaptive routing, where the switch can look at egress traffic and select among those routes to select the least congested path through the fabric. So the switch supports sophisticated arbitration. We support 16 virtual channels that can be put into multiple traffic classes. So there's tables inside of the switch that can be programmed to specify which VCs are in each traffic class. And then we can allocate bandwidth to each traffic class independently. And age-based arbitration inside the traffic class ensures forward progress as packets move across the network. So now I want to talk about fabric reliability and availability. Gen Z supports 3 different levels of CRC to ensure that packets are protected as they move through the fabric. And in the case of a link error, there's 2 kinds of retry. Link level reliability means that we can send across one single link between 2 chips, or end-to-end retry means we can send across multiple links from the sender to the receiver across the fabric. And for our optical fabric, we do not anticipate needing forward error correction, or FEC. But if it is needed, you notice it's only 2 nanoseconds. So you can look inside the Gen Z spec, and you can see that smaller fit sizes, better native error rates, and those 2 things combined allow us to have simpler ECC codes, which take a shorter amount of time to decode. So we can do all that in 2 nanoseconds. So I mentioned multiple fabric planes, right? If we support multiple fabric planes, we get not only more bandwidth, but we also get higher reliability. And what that means is any switch in our fabric can fail, and the hardware can automatically select alternate routes to work around the failure, which gives you high uptime, high availability. So we have several mechanisms to manage fabric congestion. I talked about adaptive routing inside the switches. We also support ECN, or explicit congestion notification. So any endpoint or any switch can give feedback to the requesters, and they can tell them to start throttling their injection rate into the fabric. Or those requesters, they can self-throttle as well. They're monitoring packet response times, and if that exceeds a program threshold, they can start throttling their injection rate into the fabric. Now, if the fabric does get congested and a packet gets stuck, it actually has a deadline timer, which means that packet will expire and get ejected from the fabric. And since we know we'll never have duplicate packets or ghost packets in our fabric, that means we can set lower values into our retransmission timers, be more aggressive on allowing packets to resend, and that, along with adaptive routing, means we can increase the load on the fabric without worrying about excessively long tail latencies. Okay, so that was a few slides on system architecture. Now I want to move into our optical interconnects. So a lot of times when people hear about optics, they might think long distances, like across a campus or across the country or whatever, or they might think of very expensive, maybe multiple hundreds of dollars or $1,000 for an active optical cable. In these next few slides, we want to change the way you think about optics. So the slide there is showing data rates on the x-axis, and it's showing distance on the y-axis. And be careful, the distance actually decreases as you move up the y-axis. So the area in the upper left, shown in brown, that shows for lower data rates, for shorter distances, the use of copper is just fine. Or on the bottom right, in green, it shows that for very high data rates or very long distances, single mode fiber is probably required. On the other hand, there's the blue in the middle, and I marked today's data rates of 50 gigabits per second SerDes or 200 gigabit per second links. And you can see that within the rack and the row, multi-mode fiber might be appropriate. And that's because using our technologies, we can actually be cost competitive with copper at those distances in the rack and the row. The pictures of the right are just a couple of examples. You see on the top, that's a data center that we walked through, and that's showing just how bad it can get to route copper for your cluster interconnect in the back of the rack. On the other hand is our switch module, our 60-port switch with our optical fabric, where we've integrated this all into the switch module, and we're actually exporting those fibers directly out of our switch. So you can imagine the difference in complexity and maybe power for that top versus the bottom system. So before I dig into our optics, I want to talk a little bit about the state of the industry today. So today, if I have a switch on the left and a switch on the right, and I want to connect them with optics, I might get a transceiver A and a transceiver B, or transceiver 1 and transceiver 2, and that converts to optics for me. So now the switch on the left, it activates its SerDes, the signal goes across the PCB, it goes into the first transceiver, he activates his SerDes, that activates the lasers, gets the light across the fiber. Now we get into that second transceiver who activates his SerDes, it goes across the PCB into that destination switch. So I activated 3 sets of SerDes to get a signal from the left to the right. Compare that to the HP solution at the bottom. We've integrated the optics directly into our chipset. So what that means is normally in the picture above, that transceiver has multiple chips in it. It might have a gallium arsenide driver chip to drive the VCSELs. It might have a transimpedance amplifier chip to receive the signal from the photodiodes. It might have a management chip to manage the device itself. We've integrated all those functions into our switch ASIC. So the switch ASIC has SerDes that can directly drive the optical components that are co-packaged with our VLSI. So now, think of the top picture, you're driving a signal 3 times. The bottom picture, you're only driving a signal once. And as you keep hearing, right, we're spending more data or more energy to move data than we are to compute. So that 3x helps quite a bit. So let's look at some of the speeds and feeds for the HP optical solution. We start with 56 gigabit PAM4 signaling out of our SerDes, and that's actually 53.125 gigabits per second. So you can see that we have multiple eyes that are checking between the 4 logic levels instead of 1 eye for 2 logic levels. So basically, we're setting 2 bits per symbol with PAM4. Then our VCSELs are vertical cavity surface emitting lasers. We have those in 4 different lambda, or 4 different wavelengths. And our connector can actually multiplex 4 wavelengths of light onto a single fiber. That's called CWDM, or coarse wave division multiplexing. So that factor of 4 now gets us up to 212 gigabits per second per fiber. We put 6 fibers per bundle, and now we're up to 1.2 terabits per second for that optical module per direction. The bottom picture there shows our bridge module. We have 2 of those optical connectors, so we're actually exporting 2.5 terabits per second per direction in and out of our bridge module. And on the previous slide, our switch there that has 10 of those optical modules, so it's between 12 and 13 terabits per second per direction in and out of that switch. I'm going to skip this slide for time. It basically talks about some of the equalization techniques we use to optimize the bandwidth in the channel. So that was optics. Now I want to talk about our 2.5D packaging. So as you've heard throughout the conference today, 2.5D packaging means we're taking chiplets or multiple die. Maybe we're putting those on an interposer for routing, and then we put that on an organic package. So earlier when I talked about our switch, I said that we had these cross-point buffers, for output queuing. I talked about the dedicated route tables for higher messaging rates. And we found that we couldn't fit all of that logic for a 60-port switch onto a single chiplet. So we interconnect 5 chiplets with what we call C2C buses or chip-to-chip buses. You can see we have a lot of them to carry the bandwidth we need. So now we need an interposer to carry all those signals between the chiplets. So the picture at the right shows our 5 chiplets on an interposer. You can see that this thing's pretty big, about 2.5 centimeters by 4.75 centimeters. And you can see some of the statistics at the bottom. This turns out to be a pretty big module, about 14 billion transistors, so that's sort of a modern SoC equivalent. And then look at the latency. Our fall-through idle latency is just 80 nanoseconds, which is lower than what you're hearing out of a lot of the cluster interconnect switches available today. And again, I mentioned FEC. If you need to enable FEC, that only adds 2 nanoseconds to that 80 nanosecond latency. Okay, so far I've talked about our bridge module, I've talked about our switch module. We also have what we call an E-to-O, or electrical to optical switch module. So those 3 are shown at the top. So starting at the left, to get from the compute over those electrical PCI Express buses, we bring those into our bridge. Then we export optical Gen Z to our switch. That's all optical to build out your fabric. And then to get to the storage, we want to convert from optical Gen Z to electrical Gen Z, so that's where we use our E-to-O switch. Okay, so inside of each of those, again, starting at the left, our bridge has 3 chiplets of 2 different types. and that's combined with the optical modules to build up our switch or bridge module. Then in the middle, we have 5 chiplets of one type, plus the optical modules. And then on the right, we have 2 chiplet types on that E/O module. So bringing that all together, we need 3 distinct chiplets, and those are shown on the bottom. We manufacture those with one set of masks, and we put all these on one reticle. And since you know that mask sets cost multi-millions of dollars today, doing one tape release to support 3 die with one mask set is much cheaper than doing 3 independent tape releases and paying for 3 sets of masks. Now you can see at the bottom that E/O chip is smaller, it's much simpler, so we're able to replicate that 3 times, and that'll come in, that'll be good for us since we expect to ship that chip in more volume than the others. Okay, so let's look at performance. So we're comparing our bridge to an industry standard HCA that's available today. Both of these have 200 gigabit per second links. Now you'll notice that our bridge, we have twice the connection to the CPU over those 4 PCI Express lanes, and we have twice the connection to the fabric. Now we expect to be cost competitive, especially when you compare the cost of our integrated optics versus buying AOCs on the market today. So cost competitive even though we have twice the bandwidth. So since we have twice the raw bandwidth, we can pretty much deliver almost 2x the messaging bandwidth. And again, look at that messaging rate, right? We work very hard to support a high messaging rate for unidirectional small messages. So we're achieving almost 5x the competition, almost 1,000 million messages per second. And our latency, for messaging latency, is pretty competitive relative to the competition. So as we look forward, maybe doing a next generation chipset, we're looking at going obviously to PCI Express Gen 5. We're looking at 400 gig signaling on our fabric. That would about double our messaging bandwidth, and we would expect to more than double our messaging rate, again concentrating on small message throughput. And we expect to reduce our latency to make it more competitive as well, maybe redoing some of our partitioning and shaving latency out of the RTL wherever possible. I'll skip this slide as well. This is just an example of why you might care about high messaging rates. And it's really just utilizing Amdau's law to show how a 5x increase in messaging rate might lead to, say, a 3x overall performance increase. All right, so just a couple more slides on status and next steps. So we have tape released recently, the last several months ago. We're in the final stages of wafer test and getting our chips through the value chain so that we can get them in the lab and proceed with turn-on. So you can see the picture on the left. It shows our 3 chiplet types sharing that reticle. On the top, we have our switch with our dense switch core in the middle, the chip-to-chiplet links at the top and the bottom, and the SerDes that drive the optical components on the left and the right. In the middle, we have our bridge module, or bridge chip, and what that does is it has the electrical PCI Express SerDes on the left and the right. It has the chiplet-to-chiplet links at the top and the bottom, and then all that other logic, those are the Gen Z data path slices that have the Gen Z requesters, responders, MMUs, and data movers. And at the bottom, that's our electrical to optical chip. Again, more simple chip, less logic. It has both electrical SerDes and optical SerDes. And again, since it's smaller, we can fit 3 of those in the space of one of the others. Then we show pictures of our bridge module. Again, that's a 3-die module with the optical connections. And at the bottom, we show our switch. That's a 5-die module with the optical connections. And at the top, we have the optical connectors loaded. And the bottom, we don't. And if people want to see what some of that looks like, I've got some show and tell here of these modules if you want to look at them later. Okay, then, so for last slide, our chipset team has been very busy, but our system teams have been busy as well. So starting on the left, these are the boards that we'll use to build up our system for our path forward prototype. At the top, you've got your compute board where you have your processors and your bridges. In the middle, you have your switch blades where we have our Gen Z switch with all the optical interconnects. And at the bottom, we have a storage node. We didn't really talk about it today, but there's media converters to get out to the media. And this is where we go from our optical Gen Z to our electrical Gen Z to get to those. In the middle, then, we have something called Cadet. So Cadet is an early access platform where we use our bridge and that fan out to the 12 Gen Z links. And if we put this bridge into a DL385, and then we fully connect 12 or 13 DL385s using those optical links. That's really the cadet system that we're talking about. And we're looking for early customers and partners to have access to this fully performant Gen Z system for software development, demonstration, and exploration. Now, there are other topologies we could do as well. We could build up a 4D HyperX using the bridge, and we can get to 256 nodes using that topology. On the right, we're showing how some of these technologies can be spun off into other uses. So we're showing that optical component I talked about, where we're packaging that with a simpler chip to create an E to O transceiver. And that could come in multiple different form factors. We're showing 2 of those here. The top one is onboard optics, where you can place that directly on the PCB. The other one is a pluggable. There's also Kobo form factors and things like that that we're talking about. OK, so that concludes my talk. I'd like to thank everybody in the Silicon Design Lab at HPE, HPE Labs, and the HPC group who helped contribute to this project. Yes, questions?
Satoshi Matsushita, Numeracy. I understand that your system tunnels the PCI protocol through the network, and either the configuration, how the configuration or the device discovery works on the very large system?
Yeah, so we do utilize PCI Express. It uses standard discovery capabilities to find our bridge. We have out-of-band management techniques to manage the whole system.
So we at least need a special BIOS for that?
Yeah, I don't think we need anything special. Again, it's all just standard PCI Express.
OK.
Go ahead.
Hi, this is Shaolin from Alibaba. My question is, you say it's PCIe compatible. You mean there is any overlap between the PCIe? I mean, the protocol layer, transportation layer, such as that?
Yeah, so for our data movers, all we need is a connection to any PCI Express. So we're fully PCI Express compliant. We can get all of our data move functionality using basic PCI Express. If you want to export loads and stores directly from the CPU out to the fabric, we need some extended capabilities on PCI Express. Some processors do that today. That's why we showed the Rome processor in our block diagram.
So it means there is some like you have designed your own like transportation layer over the PCIe link?
It's all PCI Express. There are some CPU vendors provide a few extra transactions that can be decoded by our bridge to export those loads or stores, but it's all standard Express plus a couple of transactions.
Thank you.
Hi, Ian Cutcherson, Antec. Maybe I missed it, but what foundry and what processor are you using?
Yeah, you didn't miss it. It wasn't in the slides, but it's TSMC 16 nanometer.
Using CoWoS.
Yes, CoWoS, yeah.
Thank you.
Hi, Alan Cantle, Molex. Just back to the PCI Express question, I was under the impression that Gen Z had its own, ideally had its own fabric, but it could use PCI Express as a transport. So have you given up doing your own fabric and you're always going to put on top of PCI Express now? Okay, so again, this gets a little complicated. So PCI Express electrical can support Gen Z electrical can support PCI Express or it can support 802.3. So for our Gen Z fabric, we're using 802.3, but we could have used Express instead.
Good afternoon, Addison Snell, Intersect 360 Research. Looking ahead to the acquisition of Cray, do you have a sense of what sorts of workloads or use cases where HPE will recommend Gen Z versus Slingshot and vice versa?
Yeah, so it's still pretty early to talk about the integration of Cray into HPE. The deal doesn't close until the end of this year, so I'm not going to speculate on what we might do as a joint company at this time.
Thank you.
Hi, it's Dongping from AMD. So I'm curious about what you mentioned, the messaging latency of 675 nanoseconds. And could you give us a rough breakdown of where it's coming from, actually, the switch, or is it coming from the electrical to the...
Yeah, the slide that talked about the 675, that's messaging latency, and that's really just talking about an HCA to bridge comparison, so we're not getting into the fabric. And I'm not going to go into more detail than what was in the slides today.
All right, thank you.
Okay, it's the last one.
Jeff Smith Citadel, and that was actually my question exactly, so I'm going to decline. Thanks.
Okay, thank you.
Thank you.
Let's thank the speaker. Jeff. Thank you. Our next speaker is Mark Wade. Mark is the president and chief scientist at Ayar Labs. Mark received his PhD from the University of Colorado Boulder. In 2015, he was on the team that won the MIT Clean Energy Grand Prize. In 2018, he received the Photonics Integrated Circuits Award for advances in photonics integration for the work that he and his team did at Ayar Labs. He's currently the principal investigator on multiple DARPA programs, and he's the co-author of over more than 50 peer-reviewed publications. Mark?
Thank you. Hi, I'm excited to be here today to tell everyone about what we've been working on at Ayar Labs. So to start, I want to recognize a lot of the people who worked on this technology. There are a lot of engineers at Ayar Labs whose hard work went into the results that we'll be showing today. And we've had a great collaboration with Intel as well, led by Sergei Shumarayev and his team at Intel. We've also been grateful to have the support from multiple government funding agencies. DARPA has been a long-time supporter for what we've been building here, as well as the Department of Energy. Now, Intel has contributed a lot to the work I'll be showing, and one of those contributions is the Intel disclaimer, so I'll flash it here and move on. So this brings me to my outline. Today I'm going to spend some time working on the motivation for what we're doing here. I'm then going to do a brief crash course in integrated optics and the type of silicon photonics that we're working on building. And then we'll start looking at putting all these things together to try to build the type of technology that we're working on. This conference has already talked a lot about the chiplet ecosystem and how that emerging ecosystem allows very interesting things to be done. So I'm going to touch on how the chiplet ecosystem has really allowed us to have a path to market and really integrate into SoC products. Then we'll spend some time talking about the TeraPHY chip. This is what we call our optical I/O chip, and that's short for terabit phi. So let's start with the motivation. So our motivation is very simple. At Ayar Labs, we believe that long-range electrical SerDes does not have a roadmap beyond 112 gigabit per second signaling. So this opens up a huge need for the industry to come up with a new general-purpose universal I/O technology to supply high bandwidth I/O to and from high-performance SoCs. Now, this is a little bit of a busy chart, but I'll walk you through it. The problem of what's happening is very clearly shown in this chart. This chart plots on the x-axis distance, and on the y-axis a figure of merit that is bandwidth density times energy efficiency. So the units on the y-axis are gigabits per second per millimeter per picojoule per bit. And what you see here is there's kind of three categories in I/O technologies that start to span this figure of merit. On the far left side, you have in-package technologies doing electrical signaling on the same package substrate, and you can get quite good figures of merit when you're electrically communicating in-package. Now, once you go to onboard communication or socket-to-socket electrical communication, you've already hit at least an order of magnitude, maybe more like a few orders of magnitude decrease in this figure of merit. But the major penalty comes when you start going off-board. And there's a massive difference between what you can achieve in package and off board. And today's production optical technologies are all in this off board category. So when you look at this, there's about 4 orders of magnitude difference in this figure of merit between the off-board communications and the in-package communications. So the question is, can we build an integrated optical solution to really address this gap? And what we're doing at Ayar Labs is building TeraPHY to try to completely remove this gap, such that you have the energy efficiency and bandwidth density of in-package communications, but you're using a new optical technology to extend its reach to many meters and up to kilometers. So let's take a quick detour into integrated optics, since this audience may not be so familiar with the field of optics and silicon photonics. So the basic building block in integrated optics is a waveguide. And here I'm just showing an animation of a silicon waveguide with an optical wave propagating down it. And you can think of this device as basically an optical wire. This allows us to direct where the light's going and control how it's interacting on the chip. So what can we do with these types of devices? Well, we can take two waveguides, bring them in close proximity to each other, and start to do things like transfer power from one waveguide to another. So now we can control where the power is going in multiple waveguides. We call this device a directional coupler. We can then take two of those directional couplers and connect them together, and connected by waveguides in between. And on one of those waveguides, we can introduce elements that can control the phase of the light, and we can then electrically control this phase. So electrical control of that phase now gives us a way to electrically control which port the light is going to, either the top port or the bottom port. What else can we do? Well, we can take these waveguides and we can wrap them around on themselves and make circles. And once we do this, we have a device called a microring resonator. And this gives us another type of device that allows us to control where light is going. We can either electrically control the device such that the light goes straight through to the through port, or it can be turned and sent to the top waveguide, which is typically called the drop port in these devices. Now, in industry, most people in silicon photonics use these Mach-Zehnder interferometers that I talked about a couple of slides ago. And when you have electrical control of the phase on one of those arms, this allows you to create devices that you can modulate up to, let's say, 100 gigabits per second per device. But the problem is these are pretty large millimeter-sized devices, so the bandwidth density that you can get and the energy efficiency is quite limited. Now, when you look at a microring resonator, shown right below it, it's about 100 times smaller than a Mach-Zehnder interferometer, and you can operate these devices at the same high data rates as people operate Mach-Zehnder interferometers. So the key here is that we have an optical device that's 100 times smaller than kind of the status quo used in industry today, and that translates into much better bandwidth densities and much better energy efficiencies. Now let's briefly talk about how we get light on and off of a chip. And we use a device called a vertical grating coupler. And this is kind of a simplified cross-section schematic of what this device does. You have a waveguide on the left that has light coming in. It's then incident on an array of point-like scatterers. And when the optical wave hits these scatterers, it starts to shoot light out of plane. You can think of this device as a phased array antenna in the optical domain. And when that light is scattered off of the chip, we can bring in an optical fiber in close proximity to the device to collect that scattered light. And this gives us the ability to take light on and off of the chip. So let's start kind of connecting some of these concepts. One thing that we've worked on for many years now is how you integrate these optical devices directly into some standard SOI CMOS processes. And what I'm showing here in the upper right is a cartoon of kind of a prototypical SOI CMOS process, where on the left and the right of that image is an NMOS and a PMOS transistor. And we can use the same silicon layers that comprise those transistors to pattern and build our optical devices. So on the left is an actual optical micrograph image of an SOI MOSFET. And the bottom left shows actual images of the devices on our chips that use those same layers to build silicon waveguides, microring resonators, and the microring resonators we use as both resonant modulators and detectors. And in the bottom right, showing our vertical grating coupler designs, which utilize the polysilicon gate of the MOSFET transistor and the body silicon of the transistor. So now I'm going to start talking about how we put this together and what some of the demonstrations we've been able to achieve look like. So first, I want to kind of walk through the anatomy of the type of optical I/O architecture that we're working on building. And it's comprised of a few main components. You have an off-chip light source that produces all of the continuous wave or CW laser light that gets sent into the chip. That's coupled to the chip through an optical fiber, and it's incident on a fiber-to-chip vertical grating coupler. That light then travels down the chip through an optical waveguide, and it goes past an optical modulator, an optical microring modulator. It then exits the chip with data encoded on it into another optical fiber, and is incident on a second chip with a vertical grating coupler, and then goes to a second microring resonator that acts as a detector. So this is kind of the basic path for all of our optical I/O. But the important thing is light has a very interesting property to where we can add multiple wavelengths of light per fiber. And it allows us to scale up the number of wavelengths that are riding down a single fiber, and we can then start putting more resonators on a single waveguide to do what's called wave division multiplexing. So each of these microring resonators locks onto a different wavelength of light, and each resonator and wavelength of light acts as an independent communications channel. But we can multiplex all of that onto a single waveguide and then onto a single fiber. Now, so far, I've kind of walked through mostly the optical path of what's going on, but the reality is you need to build a fairly sophisticated electronic system around these devices to really get them functional and reliable. So we use monolithic integration, which means we're building the electronics and the photonics on the same piece of silicon to allow us to build these electrical systems around the core optical device. So that includes things like clocking, drivers, analog front ends, all of the digital control circuitry that's wrapped around each microring resonator to actually stabilize and utilize the device. So the small size of the microring resonators combined with the monolithic integration with all of these drivers, analog front ends, and digital control circuitry allows us to hit these bandwidth densities and energy efficiencies that are incredibly compelling. So what have we done with this? Well, I'm just going to touch on a couple of demonstrations. A few years ago, we published the first CPU chip with optical I/O directly on that same piece of silicon. This was a dual-core RISC-V processor that had about 70 million transistors and about 1,000 optical devices. And the optical I/O that it used was based on the Microring WDM technology that I described in the previous slides. And the RISC-V CPU cores directly used the optical I/O on the same chip for its main I/O channel to main memory. There's a lot of details on this chip. I'm not going to walk through it here, but if you're interested, you can see our Nature paper that we published a couple of years ago. So now let's look at the exact kind of chiplet optical I/O architecture that we're working to build. Again, because we have a monolithically integrated optical I/O chip, it actually gives us a lot of flexibility around the electrical interface that we put on the chip to talk to some host SoC. So what you see on this slide on the left is a multi-chip package where there's some kind of SoC in that package, a CPU, GPU, ASIC, FPGA. To us, it doesn't really matter. We have an optical I/O chiplet that sits on that same package substrate and talks to that host SoC through some electrical interface. Now, key to this architecture is we've chosen to pursue a remote laser source overall architecture, where we take the laser and we do not try to integrate it in the same package as the SoC. We put it somewhere else as its own standalone module, and it provides all of the CW light into this multi-chip package. So you have a few choices to make, which we'll talk about more in the next few slides. What kind of electrical interface are you building? Is it wide parallel? Is it high-speed serial? Both are possible, and we've shown that we can build both of those interfaces on our chips. But it starts to also dictate what kind of package technology you're using. So I want to touch on some of the technology test chips that we've built and shown with this technology working. And this is a good chip to look at to see a lot of the core electronic photonic systems working and the kind of density that you can get. So this is a chip about a few millimeters by a few millimeters in size. We integrated 5 400 gigabit per second transmitter macros and 3 400 gigabit per second receive macros onto the same die. And again, each of these macros has all of the electronics and all of the photonics, except for the laser, that are needed to run and utilize optical I/O. If we zoom into what these chips look like, here's a zoom into the transmitter macro. And the transmitter macro is about a 0.5 millimeter by a millimeter in size. You can start to see the optical path in this level of zoom, but it's even hard to see at this level of zoom because the optical devices are so small. But we build the entire electrical system around it, clocking, drivers, clock distribution, digital backend with various debug features onto the same optical macro. So this was a 400 gig transmitter macro, about a terabit per second per millimeter in shoreline density, and about a terabit per second per millimeter squared in aerial bandwidth density. And everything in this macro comes in at an energy efficiency of 0.8 picojoules per bit for the transmitter. If we take a look at the receiver macro is slightly larger. This is where we put all of the equalization in our link. It comes in at a size of around a 0.5 millimeter by 1.5 millimeters and achieves about a terabit per second per millimeter of shoreline bandwidth density and about 500 gigabits per second per millimeter squared of bandwidth density. And the receiver comes in at an energy efficiency of around 2.5 picojoules per bit. So we've actually done lots of different kinds of technology demonstrations. We've shown that we can run our optical devices in low-speed configurations, let's say single gigabit per second per wavelength configurations. We've also shown that we can hit 100 gigabits per second per wavelength using PAM4. So these are actual eye diagrams from live running demonstrations that show with the same optical front end, you can configure those devices to run either in, let's say, 40 gigabit per second NRZ or up to 100 gigabit per second PAM4. So now let's look at how we're leveraging the emerging chiplet ecosystem to actually get this solution into real SoCs. And it's been talked about a lot today and yesterday, and in both of the keynotes this was mentioned. But almost everyone building high-performance SoCs today is looking at chipletizing their solutions. So if you're looking at Intel, NVIDIA, Xilinx, or AMD, all of their leading product lines are breaking out their digital SoC from some of the other functionality that sits around it. And since we have a single chiplet with electrical devices and optical devices, we can mostly make our chip look like an electrical chip, and we can leverage the ecosystem that's brought this to fruition and put our optical chip in that same set of assembly technologies. Now, the assembly technology that we're using and the package technology that we're using is Intel's EMIB technology. EMIB is a packaging technology that supports mixed bump pitches on the same die. So you can have regions of your die that have very dense microbumps, in our case, 55 micron pitch microbumps, and other regions of your die that have more kind of standard organic substrate package type bump pitches. In our case, 130 micron bump pitches. And how they do this is they embed a silicon bridge inside an organic interposer, and you only put that silicon bridge in the places where you need the dense die-to-die connectivity. So the next question you ask is, well, what kind of electrical interface am I going to build between my two die? And your choices are serial or wide parallel. Now, if you start to compare serial or in wide parallel, they have very similar value propositions on a few metrics. Their bandwidth densities can hit roughly the same shoreline numbers, about a terabit per second per millimeter. Their energy efficiencies both are pretty good, with the better energy efficiency going towards wide parallel and signaling at low data rates. But the big difference comes in the design complexity. It's a lot more complex to try to build these high-speed serial interfaces yourself than it is to implement these wide parallel digital interfaces. Now, because you're going to signal more wide parallel and slower per lane, you need a more complex package technology on the wide parallel case. But these are all package technologies that are commercially available today in some interposer type of configuration. And the interface that we're using is Intel's AIB interface. So this is the interface that is on today's Intel Stratix 10 FPGAs, and it will also be on the next generation FPGA coming from Intel, which is the Agile X. And the basic idea here is you try to build as simple of an I/O cell as possible, and then integrate that as densely as your packaging solution allows you to on your chip. So the simplicity results in very good energy efficiency. Today's AIB interfaces have been shown to operate at less than a picojoule per bit. And you have quite compelling latencies through this interface as well, at around a few nanoseconds. So if we go back and put this interface on the chart that I showed at the beginning, it's in the in-package family of interfaces, and it achieves a reasonably good figure of merit in the first generation. And there's a roadmap for this technology that will increase its figure of merit by a factor of 100 in the next few years. So let's look at bringing it all together and what the actual package solution looks like. Here's the 3D rendering of what this multi-chip package looks like. And the die in the middle is an Intel FPGA. Then we have our Ayar Labs TeraPHY optical I/O chiplets integrated on the left side and the right side of the Stratix 10. And we bring optical connectors directly to our chip and connect to the chip with off-the-shelf optical connectors. So this serves as our chiplet integration platform to build these multi-chip packages. So now let's take a bit more of a detailed look at the TeraPHY chip. Here's an image that shows the main architectural features of what we're building on the TeraPHY chiplet. On the left side, we build an AIB interface, and we support 24 channels of AIB, which gives us about a little less than a terabit per second of bandwidth flowing through that interface. And to the right of that, there's a layer of digital glue, and this glue performs the channel mapping from the AIB interface to our optical wavelengths in our optical macros. We have 10 photonics TX-RX macro pairs, and we can configure the exact data rate that that the optical devices are running at. So we can configure these macro pairs to run at 128 gigabit per second to 256 gigabits per second, which gives us an aggregate optical bandwidth capacity of between a terabit per second and 2.5 terabits per second. In this chip, we're building these devices to operate in NRZ mode. We like NRZ because we can operate these links natively error-free, so we don't require any forward error correction on the receive side. And if you look at the latency, it's about 10 nanoseconds, AIB through TeraPHY back to AIB, plus, of course, time of flight latency, depending on how you connect up your overall topology. And you get about 5 nanoseconds per meter of latency going through optical fibers. So one of the beautiful things here, and the previous speaker touched on this as well, is the promise of optics is you've almost fundamentally broken that distance sensitivity whenever you try to increase bandwidths. So the traditional bandwidth density trade-off all but disappears in how systems are architected today. So whether you're going centimeters of distance from socket to socket on the same board, or you're going up to a couple of kilometers, the same TeraPHY technology can span both of those, or that entire range of distances. So we estimate that the energy efficiency, all-inclusive on this chiplet, is going to come in at just under 5 picojoules per bit. And that's spread across the AIB interface, the glue, and the optical macros. So I'm going to show the physical implementation of this die now. Here's a screenshot of what the actual GDS of the chip looks like. And we can look at some of the main features here. As I said earlier, the AIB interface is built on the left. Then we have a layer of digital glue that does the AIB to TeraPHY macro mapping. And we then have the TeraPHY optical macros in the center of the chip. And on the right side, we have our optical input-output couplers. If we zoom in to what this looks like, here's a zoom in showing a TX-RX macro. And we build multiple PLLs in this macro to be able to give us a range of clock frequencies that we can utilize to run our links at different data rates. And then when we zoom into a single TX-RX slice, you really see how dense the integration between the electronics and the photonics is at this level of zoom. And if you look hard towards the top, you can see a couple of circles, and towards the bottom, you can see a couple of circles. And those are the optical microring resonators. Now, around it are things like drivers, clock distribution, integrated digital control to stabilize the rings, and some debug functionality. Now let's take a look at the EMIB substrate. This is the actual package substrate design where we've implemented our TeraPHY optical I/O chiplets. And in the first prototypes that we have today, we're putting 2 optical I/O chiplets in that package. And the location is shown on the slide here. The bottom right shows an optical micrograph zoom in of the actual package, and you can see the mixed bump density where you have the dense micro bumps, which is where the AIB interface is, and you have the less dense 130 micron bump pitch that controls that is used for the rest of the die. So here's also another optical micrograph showing the multi-chip package prototypes that we have today. And I think one interesting thing to note here is this is starting to show some of the promise of chiplet-based integration. In this case, what we're building now, there are 2 TeraPHY optical I/O chiplets. In the middle is where the Intel Stratix 10 FPGA goes, but there are 4 other chiplet areas that have different functionality that are integrated in that same package. So if you're building new types of solutions, you can look at really introducing differentiated performance into these types of things by just respinning the package rather than respinning your entire SoC. And I'm excited to show that we actually have these package prototypes with us here at the conference. These are the actual package substrates with multiple chips integrated in chiplet fashion. So if anyone's interested in looking at this in more detail, please come talk to me, and we're happy to show it. And we have some other eye candy as well with us here. Now, one thing that we're really excited about is if we build this optical I/O inside the package, and we remove that fundamental distance trade-off in the bandwidth distance trade-off that you have today, it opens the door to really build architectures at the system level that are just impossible to build with today's limitations on electrical I/O. So we're looking forward to working with the community to figure out how to build larger and larger, logically connected but physically distributed systems, enabling optical connectivity at the shelf, the rack, and the row level, all through the same physical technology. So with that, thank you for your time, and I'm happy to answer any questions.
Yes, go ahead.
Hi, one of the big concerns is how do you align the fiber up to your chips? The single mode fiber aperture is, what, 8 microns or so? How do you solve that problem?
Yeah, so single mode fiber is a little above 9 microns in size. So in what we're doing right now, we're leveraging off-the-shelf components that have been built for the optical transceiver industry. And then, especially at the 100 gig generation, where optical transceivers saw a huge volume increase in the data centers, there's already tooling that does the alignment for these types of components. So you can get half micron alignment accuracy with that tooling today. Is that active or passive? So right now we're doing active. Takes a few seconds to actively align. It's not at all the time that dominates the total alignment. It's usually the UV cure that actually dominates the time to attach a fiber. Yeah. Yes.
Paolo Farabaski, HP. You haven't talked much about the external laser to drive the power, the optical power. And I'm wondering whether your 5 picojoule number includes the power for the external laser, and if not, what it would go up to.
Yeah, so this talk was focused on the TeraPHY optical I/O chiplet. And the external laser, we've built those prototypes as well. And there's actually several vendors who can now build that technology. So the first comment is because you've separated out the laser, you've really relaxed the kind of constraints and the system level constraints required around managing that laser. The 5 picojoules per bit here was quoting the all-inclusive number for the actual chip sitting inside the package. Now, depending on who you go work with to build that external laser, you're looking at adding another 1 to 2 picojoules per bit on top of that 5 picojoules per bit number. But the important thing is you've separated that out somewhere else, and you can deal with it in a different physical location.
Thanks a lot.
Yeah.
Ken Chen from Xilinx. Very good talk, by the way. My question, similar to laser, my question is really in the ways of WDM. You were quoting like you can have 64-way WDM. Have you found the source of a laser that provides you that many wavelengths?
Yeah, so today, I put 64 up there because we feel like this is a...
Oh, let me just say 32. I mean, have you...
So 32, there are some kind of low volume solutions at 32 wavelengths. What we're building first is an 8 wavelength solution. So in our macros, we're choosing to build 8 wavelengths, and that is commercially kind of available today. There are people building those types of lasers today. Now, if you go to 32 and 64, it seems like you can build those, but that's an R&D roadmap with lots of people working on the laser problem to figure out how to efficiently build 32 wavelength, 64 wavelength lasers. So it's not something that's available today, and we feel that 64 is a reasonable kind of upper limit to how many wavelengths and how many channels you can get per fiber, let's say within the next decade. But it's certainly not commercially available today, although there's a lot of promising research in the optics community.
Thank you.
Just a quick question on the noise and thermal sensitivity of doing something like this in this SOI process and the tuning knobs that you might have or constraints that you might have, if you can comment on those.
I didn't quite catch the question. The comment on the thermal sensitivity?
Yeah, thermal as well as just noise sensitivity, right? Electrical, power noise, et cetera, between the high-speed SerDes and the optical, micro-ring resonators being on the same.
Yeah, so let me touch on the thermals. So one of the main reasons why we pursued an external laser architecture is because we're assuming that inside the SoC package, everyone we're talking to building kind of advanced SoCs is talking about running those devices, let's say, north of 90 degrees C. So the CMOS chiplet that we have in this multi-chip package, this is a Global Foundries chiplet that's coming from a process that's already been qualified at -40 to 125 C. And then we build thermal tuning control loops inside our micro-rings to closed loop track the thermals that are happening on the die. So we can dynamically track the thermals as they change, and we have a very large thermal tuning range on those rings to cover the entire range that we expect to see in the package. On the noise comment, we're currently working on characterizing exactly what that looks like, but I will say that our SerDes, we're not building kind of long-range SerDes that really are super power hungry, that can be swinging lots of power there. So it's an active thing that we're working to characterize right now, but I don't have a final answer for you.
Okay, this is going to be the last question.
Hi, Alan Cantle, Molex. I may have got confused, but I thought I saw 24 electrical transceivers going into your device and then 10 optical outputs from it. Did I misunderstand that?
Yeah, so there are 24 AIB channels, but then you have to go look up the details of how an AIB channel is spread across many wires. So, but the short answer is we have kind of a wide parallel set of digital data coming into the chip. In this generation, operating at 2 gigabits per second max per wire. And then we serialize that up on our chip to go to a higher data rate per wavelength on the optics. So we have wide parallel coming in, we serialize it on our chip, and we ship it out optically.
Okay, let's thank the speaker.